Sorry, though, like, look at a movie and just be like, I could look at this fake world.
Do you empathize with the vocabulary?
What's that, the fake name? I'm just kidding. It's a big word.
You are so much like the birds you study.
So much like
Ruthless.
The drone.
Yeah, I was gonna say, what do you mean?
Yeah,
bird?
from the government.
Yeah, from the government.
Charges on cell towers. It's like they land on phone lines.
Maybe I get a little too. Like, pick what I watch.
All right, so
Try too hard to be unbiased.
okay. All right, so we got two-way ANOVA. This is kind of go through the theory and then practice on how to interpret it. So again, we've got a measurement variable, but then we have two independent variables, and we're interested in the effect of those variables on that dependent variable. What we're going to use, or one of the reasons why ANOVA is so powerful, is that we can partition out the variance and assign it to the different components of our model. So with our model, we're going to have main effects terms, which are those variables themselves, and then what's called an interaction term. And that is the effect of both of them together. All right, so you can say, well, are these main effects affecting height together? Like, yeah, but each one affects height in its own way. What we're talking about here is the effect of nutrients based on what level of day length we're dealing with, or the effect of day length based on how many nutrients we're talking about. So this is our interaction effect, where one affects the outcome of the other. All right, one variable influences the effect of the other. That's our interaction effect. So our partitioning is partitioning these sum of squares terms. All right, so all of these sum of squares for each of the main effects, for our interaction term, and that residual, that error term, is going to sum to our total sum of squares, the overall variation in our data set. What we then do is scale those sums of squares by their degrees of freedom to obtain those mean squared terms. And if you recall from ANOVA, the ratio of the mean squares, the ratio of our treatment mean squares to our error mean squares basically gives us that F ratio, that statistic, that test statistic that we then use to determine, did we explain a whole lot of variation with our variable, with our term. All right, so you've probably seen tables like these through your undergrad. Right? You've probably seen tables like these in some research papers. Typically, I've seen them in like psychology, social science type papers where they tend to be required. Not so much in our biology journals. All right. So how do we get these? Well, we get them by using the function ANOVA, and we've got two of them. We have the one that's in the base package, and we have the one that's capital letter. And if you remember, I was stressing to use this one with the capital letter that's found in that car package. Why is that? It's because this ANOVA table, there's three different types of ANOVA tables. All right. So our ANOVA tables can be broken down into a type 1 or a sequential type of sum of squares table, a type 2 table, which is a hierarchical sum of squares table, and a type 3 table, which is a marginal sum of squares table. All right. So the base package that has this lowercase ANOVA does a sequential sum of squares. And what that means is that it's going to start with the first term in your model and calculate the p-value, or calculate its effect. And then it looks at the second one and calculates its effect after we've already accounted for the first. And then it goes to the third term and calculates its effect, its p-value, after we've accounted for the previous two terms and so forth. So what we could do with the sequential sum of squares is change the order of our variables and get different p-values. All right? And we'll come back to that idea. This could be important if we have, let's say, a covariance. If we know, for example, some variable is correlated with our dependent variable, we're not necessarily interested in that effect, all right, but we want to account for it. All right. So what we would do is use a sequential table so that that term goes in first, we account for it first, and then every subsequent variable, the p-value is after we've removed that effect of the covariate. So example could be looking at, let's say I'll use fish. All right, you're looking at the difference in infection intensity between male and females. All right, we know that infection intensities are correlated with size of the fish, with age of the fish. So what we could do is remove the effect of age or remove the effect of size, and then investigate if sex differs, if intensity differs between the sexes. This is something we'll do. We'll talk about this and we'll go over it, and I'll show you examples as to why it's important to do this. The type 2 tables, hierarchical sums of squares table, is the default option for this capital ANOVA. All right, so you don't really have to do anything, it's default. What it's going to do is calculate the p-value of our variable after accounting for all other terms of the model. So I'm going to go back to here, all right? And if we're interested in this p-value of nutrient and day length, what this is the p-value after we've accounted for the other one. Now the catch is that it only accounts for the other variables at the same level or below it. So for nutrient and day length, this only accounts for these two because they're at the same level. It doesn't account for that interaction term. If we added a third variable, we'd have 3 of these, then we start having more of these interaction effects. So the p-value of the interaction effect would be the p-value after we've accounted for all other two-way interactions along with the main effects. This two-way or this type 2 table is going to be the one that we typically use because we're trying to figure out which terms can we remove and drop from our model. It's that form of model simplification, and again, we'll talk about it. Catch, if we have a significant interaction, we cannot interpret those main effects. And we'll come back, we'll see this, we'll do this. The third model is a marginal sum of squares. This is the type 3 sum of squares table. It's accessible with capital A, but you have to specify the type. The type, you can do the 3 I's, Roman numeral 3, or I believe you could also do the number 3. This affects the p-value after all variables, after all coefficients are accounted for. So the main effects would be p-values after you account for the interaction terms and so forth. But that's not necessarily right because if you have a significant interaction, you can't look at the main effects. We have to analyze the main effects in a different way. Some places will use it. I'm going to say don't use. Don't use this type 3 at all. Use the type 2. If you have to, use the sequential sum of squares. Now, if we have a balanced design, meaning we have equal sample sizes across all of our groups, and this is not just like equal sample size in male versus female, but if we had male versus female fish and we had species, you had the same sample size of male species 1 as female species 1, as male species 2, as female species 2. Basically, all of the combinations put together a single group classification, you have equal sample sizes just across the board. If we have that situation, then in theory, all 3 models should generate the same p-value, which means the ordering doesn't matter. All right, the order of our variables doesn't matter. And again, we'll come back to these ideas with our examples, with our interpretations. All right, so which one should we use? I just said my recommendation is type 2. That's my default anytime we have 2 or more independent variables. That's my default. Now, we can get around that if we have certain characteristics of our data set. So for simple models, when you have only one independent variable, like a regular ANOVA, you can get by with using the lowercase ANOVA. You're going to get the same p-value as if you use the capital one. If you have a simple two-way ANOVA and it's balanced, meaning equal sample sizes for all your groups, yeah, then in theory, we should get the same p-values for both of these. All right. If, however, we have a covariate and we want to remove the effect of that covariate and then analyze the rest of our data, then you're going to likely need to use this ANOVA, the lowercase. Although, again, conceptually, type 2 will also work if we set it up correctly. Actually, no, it won't, because we want it to go in first. Yeah, if we do an ANCOVA, you'll see. Our variable has to go in first, and we ignore the p. We basically ignore the p-value, or if the p-value is not significant, then generally the covariate can be dropped. So we'll talk about that. Type 2, more complex models. If you have 2 or more independent variables, use the type 2 tables. Type 3, don't use. Now, conventional thinking as to which ones used, it's really complicated. All right, you're going to find recommendations all over the place. Feel free to research it on your own time. Don't blame me if you start bleeding from the nose and mouth from all of this. Okay? All right, so we're going to work with the two-way ANOVA, and we're going to work through this idea of simplification. All right, we want to pick the model that explains the most variation with the fewest number of variables. That's our goal. All right, if we have a variable in our model that doesn't really explain a whole lot, isn't important, we want to drop it. So how are we going to simplify our model? Well, this is the general procedure, just kind of like the overall general procedure of any form of model simplification. We start with our full model. All of our variables, all of our interaction terms. All right, and then we look at that full model, and we look at the highest order of terms, which is in most cases our biggest interaction term. That interaction term that has all of the variables inside of it. If that's significant, that's a significant term, then you have your simplest model, which is that completely full model. But if it's not significant, then what we do is we drop it from our model, we drop that big term, and we start looking at the lower interaction models. All right? So, I think I could do this. Let me just kind of diagram out some models and just kind of show you this basic process. All right, so we're going to use A and B. We have some model. All right, two-way interaction term. This is two-way model. We've got our main effects here, A plus B, and we have our interaction term. We make this model, we look at the interaction term. If it's significant, this is our model. This is our simplest model. It explains the most variation. If it's not significant, then what we do is we drop it out, drop that interaction term out, and we look at our main effects. All right, so now we look at this model. And we ask, is A significant? Is this a significant predictor of Y? Is this a significant predictor of Y? But what we're going to do is use a two-way or a type 2 sum of squares table, because we want to account for A before we look at B. And then we want to do the other one, which is we want to account for B and then look to see if A is significant. All right. If we have a situation where on that type 2 table B is significant but A is not, then we drop A. And we look at that model. If A is significant but B is not, then we drop B from our model. All right? If neither of them are significant, Then we drop the one that has the largest p-value and look at that lower model. All right, if neither of these have a significant p-value, then we simplify it even more, and we get to what is called our null model, which is a model that doesn't have any terms in it. It's a null model because what we use is the overall mean as our predictor. All right, so for parasite intensities, we have fish species and sex. Perhaps if we had the null model, all that we do would take the average intensity across all fish and say, that's our prediction. If we catch a new fish, we predict it to have an average number of intensity. But if we have any of these significant terms, then we use this information to make our new prediction about what the intensity could be. All right. Now, what happens if we get significant terms and we simplify the models? Well, we're not quite done, because what we have is the possibility that these variables have more than two groups. So in those cases, we have to go that next step to investigate what those relationships are. So sex is easy. If sex is significant, you look at averages or effect sizes, male versus female. Say we look at whichever one's larger. But if we have three species and we know that species is an important effect on intensity, we have to go that next step to figure out, well, what is that effect? Which species has the highest? Which species has the lowest? Which ones are different? Which ones are not? And so forth. So it's the same type of thing that we've been doing with the ANOVA. If it's significant, we have to do a post hoc test of some sort. All right, so what we're going to do is work through a problem using the cabbages data set. This is in the mass package. All right, so we can access it a couple ways. All right, we'll go back to some of those early introductions to R. I show you how we can access it, or you can load the mass package. Load the mass package, and then when you type cabbages, it appears. It magically appears. All right, so that may. Oh. All right, so I am getting. R marked down. Speaking of which, how'd the homework go? Any questions? So just, I don't know if anyone's watching. If you ran into an error that said QQ plot not found, function not found, there's the reason. When we knit this document, it starts with a completely fresh instance of R. Nothing is loaded, no data is loaded, no packages are loaded. So at the start of these homework files, at the start of these exam files, you will see a data chunk, a library chunk, or like a combination, data and library chunk. When I click on packages, what you have probably been doing is going down, finding these packages, and here's clicking on mass to load it. What you probably didn't notice was this. That pops up in the console window. You need that code to be copied and pasted up here. Now, it always works for me when I do just library and mass and don't include the location, but that has to appear near the start, or at least before we access cabbages. All right, so if I try to run cabbages right now, crap, let me uncheck it. Get it detached. All right, so if I run cabbages now, I'm going to get object cabbages not found. You may have had object species worm not found. Because the same thing applies to the data frame. You have to have that code that imports a data set into that markdown file first. But if I put this library mass in the chunk and then run it, now it's available. All right. So just remember, make sure you have the code that reads the data file into R and these library functions into your markdown document, and it should. All right, so I've got my cabbages loaded. We can do a plot. Can't see it. Let's do this. Here it is. These are our names: cult, date, head weight, and vitamin C. We already went through it last week. You measured cabbages. You had 2 different cultivars of cabbage. You had 3 different planting dates for the cabbages. All right, and then at the end of the time period, they measured the head weight, and then they measured vitamin C concentrations of those cabbage. All right. So what they're interested in is, does cultivar or planting date affect the overall vitamin C levels? We did interaction plot. That's in our base package. All right, and it needs an X factor, a trace factor, and a response factor. All right, so I can use cabbages, $cult, cabbages, $date, and cabbages, $byte C to produce this interaction plot. And I think it works okay. But it gives us this type of plot where it says, okay, well, cultivar 52 seems to have higher values of vitamin C than cultivar 39, regardless of the planting date. All right, if we look at planting dates, it looks like day 21 has the highest vitamin C across both cultivars. Day 16 is in the middle, and day 20 has the lowest. All right. So what we want to do is analyze these data to see, is cultivar an actual predictor of vitamin C levels? Is planting date an actual predictor of vitamin C levels? And is there a significant interaction effect? Now, graphically speaking, if there is a significant interaction effect, then these lines on the interaction plot should be parallel. Did I say if there is an interaction? Yeah. If there is an interaction, then they should not be parallel. They should not be parallel. If there is an interaction, then they should be parallel. Because if they're parallel, then the relationship between the dates persists regardless of our cultivars. The relationship between the cultivars persists regardless of our planting date. But you can still have the main effects. You can still have differences between the dates and between the cultivars. So, what we're going to do is we are interested if any of these things influence our vitamin C levels. So we start out with testing an interaction effect. And what that interaction effect is essentially doing is taking our data and looking at the individual groups. And our individual groups now is every combination of cultivar and date. So I've set it up. So we are going to look at the means and compare them. So here, the cultivar 39 day 16 mean is equal to the mean of cultivar 39 day 20, which is equal to the cultivar, or the mean of cultivar 39 day 21, which is equal to cultivar day 16 mean, which is equal to the cultivar 52 day 20 mean, which is equal to the cultivar 52 day 21 mean. So you had 2 cultivars, you had 3 dates, you got a total of, 6 different groups. 6 different individual groups. So our interaction effects, basically testing, are the means of these 6 groups equal, or are they not equal? All right, so how do we approach this ANOVA? How do we approach these two-way ANOVAs? Well, the assumptions are the same as our regular ANOVA. First assumption is that our data are random and independent. All right, we design our experiment around that. Second assumption is that we have normal distribution across all of our groups. And all of our groups is each combination of our independent variable. All right, so this cultivar 39 day 16 mean for that subset is normally distributed. This subset, the 39 day 20, is normally distributed. This subset, cultivar 39 day 21, is normally distributed. 52, 16, and so forth. All of those individual groups are normally distributed. QQ plot and writing the formula isn't going to work. Unfortunately, not going to work. We're going to have to do that manually. And then our third assumption is that our variances are equal. And again, our variances being equal mean that this group variance is equal to this group variance, which is equal to this group variance, and so forth. The beam test and Fligner test can do it. Fligner test takes a little bit more. So, what we're going to do is check our assumptions. If the assumptions are met, then we're going to create our model, linear model, using this type of format, and we can simplify by using the multiplication sign, and R will automatically separate our model into something like this. Makes it easy. And then we look at the ANOVA table. All right, so our model is going to have main effects, which is the effective cultivar only, and the effective date only. And then it's going to have the interaction effects. And the first thing we're going to look at is this interaction effect. All right, so how do we assess our normality? We're going to use a complex logical function. Now, we've already done this. We've already done this when we did our pairwise t-tests. All right, when we did the pairwise t-test, we did OR because we needed to extract two groups. We're not going to do that. We're not pulling out two groups. Instead, we're specifying two variables, and we're specifying what both of those variables have to be, what levels they have to be. So instead of using the OR, which was the pipe symbol, we're going to use the AND, the logical AND, to have, and we use that with the ampersand, the AND symbol. All right. Just to note, we're also using the double equal sign. That's our logical for equal to. If we were doing something for like if it's not equal, it would be exclamation point and then equal sign. Are we going to use that? Highly unlikely. All right. So general procedure for doing this is to look at the levels so that we know what to include in our subset function. All right. We can access that using the levels function. Then we're going to determine all possible combinations of our treatment groups. All right. We need to know that. Short way to figure out how many is the number of levels in variable 1 times the number of levels variable 2. That's how many QQ plots you will have to make. All right, and then you'll make your QQ plot, and what I like to do is just put it all within a nested subset of commands. So QQ plot on the subset data where we only look at one variable. All right, so let's do this. All right, so we're going to look at levels. So we've got levels, cabbages, date, and levels, cabbages, cult. All right, so I'm going to run this chunk to get our different combinations. So we've got 6 total combinations to make. All right. And then from those 6 combinations, what I'm going to do is start getting my QQ plot. So our function is, again, QQ plot. All right. And I need my library. So I'm going to put library car right at the top so it always runs. I knit, roll down. All right, so I'm going to use the subset function. Now remember, the subset function is going to return a data frame. All right, and it's going to return a data frame just but only those rows that we've selected. In that data frame, we'll have that vitamin C variable. That is our dependent variable, so that's what we're going to make our QQ plot. Now, what are the levels? Well, we're making a subset of the cabbages data set. All right? And we want every combination of date and cultivar. So, we want to specify our date. All right, so we want to pick out the date that is equal to, we'll start with D16. Now, these are nominal text-based variables. Since they're a string or a text, we have to use quotes around that value. So with this subset, we're basically only looking at day 16 cabbages and looking at vitamin C. But that's not the assumption. The assumption is normality with every possible combination. Since we have date and cultivar, we have to go that next step and also include a cultivar selection. So for our cultivar selection, I'll start with cult equals D39. So this subset will pull out all of those rows that match day 16 and cultivar 39. So just to kind of demonstrate this, I'll highlight the subset, and I am going to run. Hopefully that selection only gives me the data frame. Yep, that's your data frame. That is it. Day 16, cultivar 39. That is the only thing that subset puts out. Now we have it, because that's exactly what we want. So now we look at our QQ plot. So this is QQ plot of 1 out of the 6 of our groups. Now this works. This code works. So now what I'm going to do is update this and look at all the other 5 combinations. All right. So using this code, go ahead and try to do that. Go ahead and try to do that. And the order doesn't matter. So on the next slide, I have QQ plot, subset of cabbages. I switch the date and the cultivar. Okay. Doesn't matter. All right, what order they appear. We've set up the logical. Only look at the cultivar 39s and day 16s. Copy and paste is your friend. All 6? Everyone be one? Here's how I would approach it. As I said, copy and paste is your friend. Start dates. And do day 16, day 20, day 21. Those are all cultivar 39s. I'm going to highlight those 3, paste them, and then switch these to 52. And now I can run this, and with the R markdown, you can see it puts all 6 up there. So now I only have to just kind of cycle through these by clicking on them to see all of them. Now, what do we see? Sample size is pretty low, right? 10 items per group. This is what we would call a balanced design. 10 items in each combination. All right, so looking at this, do you think it's normally distributed?
Yes.
Yes, it's bad. Yeah, it's sample size of 10. They look pretty good. I mean, it's really got to be like way out there with sample size of 10. All right. So next up is the equal variance assumption. Normalities have met, so we can run Levine test or Brown-Forsythe test. And Brown-Forsythe is really easy to do. All right. It takes a formula. And just like a linear model, we can give it the formula and use the multiplication sign, the asterisk, and R will expand those and look at equal variance across all of our groups. Right, so I've got code already up here. Run it. You should get the same p-value. F statistic p-value. Did you get it? Same thing? All right, while we're at it, maybe go ahead and try the Fligner clean. So let's say you ran something and it's like, well, maybe it's not normal. Let me be cautious and run the Fligner clean test. Did it work?
No.
No, it doesn't. No, it doesn't. So in the Fligner test, it is looking for vitamin C as a function of one of these variables. That's what it's looking for. It can't. It doesn't know how to handle, these interaction terms or how to expand a formula to include all of those terms. So for this, we have to kind of do a trick. We have to make our own variable, our own combination. One of the short ways to do it is to utilize the paste function. Paste function and read it into a new variable, just made up variable. All right, so what the paste function will do in this case is takes the value of cabbages, $cult, whatever is in that column, and combine it with whatever's in the date column. All right, so I'm gonna use paste these two columns. If we had 3 variables or 4 variables, I just keep adding them on. All right, so when I run it, if we were to look at what that x1 looks like, you're gonna see that it's basically just combined C39D16, C39D16, C39D16. So we basically made our own combinations. This will work because we took 2 variables where it was 2 levels and 3 levels and made a single variable of 6 levels total, which is exactly what we were doing with QQ plots. So once that is made, now I can use the Fligner.test vitamin C is a function of that variable that we created, x1. I called it x1. And you can call it whatever. All right, and now it works. If you don't think that works, try your Levine test again. But use x1. Oops. And you'll get the same p-value, same test statistic, and everything. So it works the same way. So again, just kind of a shortcut method to be able to use this Fligner.test. How often do you really have to do this? How often do you only have 2 independent variables? How often are both of them categorical? That kind of tells you what we're looking at. All right. So now that we have this, it appears that all of our assumptions are met. Right? So data are random and independent. We'll assume that that's the case. That's how we designed our experiment. Were our data normally distributed within each combination of treatments? Yes, we did. We checked all 6. Did we have equal variation or equal variance in each of these groups, these combinations of treatments? Yeah, we did. We used Brown-Forsyth, and we demonstrated that Fligner-Kleene would do the same thing. So now that all of our assumptions are met, we're going to run our 2-way ANOVA. All right, and we start by creating that linear model. All right, so the linear model is going to do this, all right? And this is kind of a little bit more into what's going on and helping us get to our summaries. So we're going to create our linear model, and I'll do this over in our markdown. So I'm going to just call it mod 1. Actually, I'm going to do mod full, because this is our full model. So we're creating a linear model where we are predicting vitamin C as a function of cult times date, where all of those are found in the Cabbage's data set. All right. So that's going to create our model, our full model. Why is it full model? Because we have our main effects and all interaction terms. And we accessed it. This is asterisk. R is going to do all the expansion for us. Now, what is it doing exactly? Well, what it's going to do is to try to create an equation, a line, a best fit line that matches our data points, or matches our data points for all of the different levels. All right, so if you have just the simple x as a function of y, and I think we talked about this before, what the linear model is going to do is kind of take a look at the graph of all your data points and try to figure out the line that minimizes our residuals. And the residuals is the distance between each of our data points and that equation for the best fit line. All right, we can extend this to do additional variables. So if we added a second variable, this isn't necessarily a straight line anymore. This is actually more of a plane, a 3-dimensional plane. So we're trying to fit the plane on one axis, that would be, let's say, cultivar, and then we're fitting the plane on the other axis, going back, which could be date. All right? R handles this for us. You don't have to worry about it. And what R is going to come up with is an equation where we have our y term, that's our dependent variable, and then we have all of our x terms. Now, what we have are coefficients. R is going to report coefficients. So we've got B0, that is our intercept term. That's just our overall terms, where we're going to cross our 0 points. All right, and then we're going to have coefficient 1. And that coefficient basically says this is the effect of our first variable. All right, this is how much we increase or decrease. How much we increase or decrease our intercept. And then we're going to have a second coefficient, and that's corresponding to our second term. And then we're going to introduce our interaction terms and so forth. And we keep going until we have all of our coefficients made. And then we have this error that's like everything left over that we can't explain yet. All right, that we can't explain. Now, if we're working with continuous variables, then this works out pretty easy. These coefficients represent the slopes, just like the slope of our line. But if we're working with categorical variables, then what R is going to do is create a new variable called a dummy-coded variable, where it takes however many categories we have, take one of those categories, puts it into our intercept, and makes a coefficient for each of these. So I've depicted this here as pretty simple. We've got three coefficients. We've got an intercept, we've got a cultivar, we've got a date, and then we have this interaction effect. With nominal variables, our number of coefficients start to increase quite drastically. Because for cultivar date, yeah, we're going to have the intercept and we're going to have our one coefficient for that second option. But for date, one of those dates is the intercept, and then we're going to have a coefficient for day 20 and a coefficient for day 21. Why is that important? Because some of you have already come to me and says, I need to know what sample size I need. I need to know how much data to collect. And I've always said, rule of thumb is 5 data points per variable. The actual one is at least 5 per coefficient in our model. So if you have 5 levels, we're not talking about sample size of 5 across all those levels. All right? We're talking about sample size of 5 times those 4 coefficients coming from this dummy variable. And you're going to see this in our summary. All right? So the way R does it is takes these dummy coding and alphabetizes the levels. The first one goes into our intercept. All of the others become a coefficient. All right? And those coefficients then tell us how much we're going to increase or decrease the averages. The interaction term is going to fall the same way. It's going to take both of those terms. You know how I did that Fligner test and we made day 16, cultivar 39, and so forth. It's going to do the same. It's going to do the same. So just to kind of demonstrate this, we made our full model. If I looked at the summary, you will see we have more than 4 coefficients. We've got our intercept. That was our B0. All right. So that's like the overall average of vitamin C levels across all of our data. But it's not the overall average because we've dummy coded our variable. This is the average for cultivar 39 and day 16. Can I prove that? Yeah, of course. Of course I can. I can use my aggregate function just to prove that. Oops. So we used it in a simple case. Does aggregate work? Yep. What did I say? Day 16, cultivar 39, 50.3, right? What was the summary? 50.3. There's our average. And then the next coefficient is cultivar 52. All right, so this is cultivar 52, day 16, but not quite, because we have to account for cultivar 52. We'll add 12.2 units. And then we need to have, day 16, cultivar 52, add 12 units, 62.5. All right. What if we wanted to look at cultivar 52, day 20? Well, we're going to account for this, cultivar 52. We're going to add 12.2. We're at day 20. We're going to subtract 0.9. And then we have this cultivar 52, day 20. We're going to have to subtract another 2.7. What's our average? 58.9. And you can just kind of do all of your addition and subtraction and come up with the same average. So this is our best fit equation. R does it for us and says we're going to minimize the error around this best fit equation. And this is what we get. All right? All Alright, so this kind of is showing you this dummy coding. I went a little bit more in depth about the matrix. We probably won't be doing that at all. Alright, but if we wanted to change our groups, we could. We could dummy code it ourselves. We're not. So consider this stuff kind of background information, FYI stuff that kind of says this is what's happening. This is why we don't see cultivar 39 in day 16. It's built into our intercept because of this dummy code. All right, so let's look at this summary. This is what's starting to get important for us. All right, so here's our summary of our model. All right, and this one I called it model. I didn't call it mod full. All right, we've already mentioned our coefficients. For us right now, we don't really need them because we could easily just use the aggregate function to get our averages. What we're interested in is these two lines here. All right, so this F statistic gives us 15.39 on 5 and 54 degrees of freedom, and it gives us a p-value. What is that F statistic? What are we testing? This is testing against a null model. All right, that's what it's testing. So we have our full model. Space. So we've got our cult date and cult and date interaction. That's our full model. It's comparing to this one, to our null model. Did we do better by including these variables than if we don't? So if you get a p-value that's greater than 0.05, your model is no better than the null model. None of your variables basically have an effect. But here we know we've done better. By accounting for cultivar and date and the interaction, we've done better than just looking at the grand mean and predicting our vitamin C levels. That's a pretty good thing, usually, in terms of doing science experiments. The other thing is this adjusted R-square. This adjusted R-square term tells us how much variation is accounted for by variables in the model. And you can say how much variation of what? How much variation in vitamin C? That's what we're looking at. We've accounted for almost 55% of the vitamin C levels, or the variation in vitamin C levels, by including cultivar date and that interaction term, which is pretty good. Right? We still have 44% that's unaccounted for, but we've accounted for 56%, or is it 55? 55. So 45% is unaccounted for, 55% is accounted for. Now we have a multiple R-squared and an adjusted R-squared. I'd go with the adjusted R-squared because the adjusted will account for sample sizes. All right, so it's one of those things that sometimes they're going to be really close, other times they're far. Like this one, 59% versus 55%. I just use the adjusted R-squared. All right. So does this tell us if the interaction term is significant or not? No, it doesn't. What this is just telling us is that we've accounted for quite a bit of variation, 55%, and we're better than the null model. What we have to do is generate that ANOVA table. All right? And we do that with our capital A. So this interaction term here, use ANOVA of our mod.full, and the default is a type 2 table. So what this will do is we start at the highest level, at that interaction term, and we look at the p-value. This p-value is the significance of this interaction term after we account for cultivar and date as the main effects. All right? So is there a significant interaction term? Are the slopes of our interaction plots parallel or not? All right. In this case, p-values greater than 0.05, yes, they are parallel. We don't have this interaction effect. We don't have this complicating factor to deal with. All right? So this is comparing, this interaction term is basically comparing our regression slopes. The slopes of those lines on that interaction plot. And that's what I have here. So if it's not significant, there's really no reason to include it in the model. We want to get to the simplest model, which is the model that accounts for the most variation using the fewest coefficients. All right? So we know the full model is better than the null model. We just showed this. But is the model too complex? So far, yeah, we know that the interaction term is not significant, so we shouldn't really include it. So how are we going to simplify? We've got a couple different methods. We've got classical tests, where we use f-statistics or log likelihood methods and calculate p-values. All right? Right now, we're going to learn this one, because I'm going to show you how it works out doing a simple two-way ANOVA. And you could do this also with a three-way ANOVA. Once you start going above that, it becomes too tedious to try to use these tests, which then means we're going to fall back on one of these other tests. All right? There's randomization tests, where we basically create two models. We calculate f-statistic between them, all right? And then we generate our own null distribution of that f-statistic. You've done some of this permutational ANOVA. Sometimes it takes a while to run, right? Doing the pairwise test takes a while to run. This takes a while to run, all right? We try to avoid this unless we are forced to do that, all right? When might we be forced? We violate our assumptions. Right? If we violate our assumptions, we can't do our regular ANOVA tables. All right? In that case, you can do this third method, this information criteria. But if someone takes issue with it and says, no, I want to see p-values, you've just forced it. So that time when you're going to be forced to do this, you violated your assumption and you have some reviewer that says, no, I want a p-value. You're going to have to do that. I'll show you how we can do it. I think I do it here. But for the most part, we're going to run our classical test. You're going to see how that's done. And then we're going to rely on this information criteria, AICs or BICs, which will get us down to the simplest model. Now, if our assumptions are met, all three will give us the same results. All three will give us the same simplified model. All right. If we violate the assumptions, the randomization test and the AICs will give us the same model. These won't because, again, we violated our assumptions and we can't use them. All right. So that kind of means then, well, if these come up with the same conclusions, even if we violated the assumptions, let's just stick with these. And if you're wondering, how many people actually use it, go ask Cameron how she's simplifying her models. You might actually have to take her to dinner first, like take her mind off it. All right, but we'll learn both. All right, so the classical test is going to use either an f-test or a log likelihood method. Which one we use depends on the type of ANOVA we're running. So typically it's going to be just the f-test because it's a two-way or three-way ANOVA. But if we do, let's say, logistic regression, or if we include some random effects in our models, then we're going to have to use the log likelihood method. All right, so how do we do this? Well, it's pretty easy. We make our two models. We make our full model, or we make a complex model, and we make a simplified model. And then we issue the ANOVA command on those two models. So ANOVA of our model 1, ANOVA of our model 2, and that'll test the significance of that term that was dropped from our model. All right, so what we need to do is make sure that we're only testing a single variable. Right? One term appears in, that variable appears in one model, it does not appear in that second model. We can also use the capital A, all right, but we'll get the same answer. All right, we'll get the same p-value. All right, there is a catch though. If we're going to do this method, then we can only compare nested models. And what that means is that our full model is a basic, let's see here. The nested model means that our models have the same terms with the exception of a single variable. All right. So the simplified model is a nested version of the more complex model. We can't compare. So I should say, let's get this. This is a nested model, believe it or not. So we can do this one. That is a nested model of this one. These two terms appear in that model, right? This is a nested model of this one, and it's a nested model of this one, right? Because the terms are still in there. This one is a nested model of this, and it's a nested model of this. Again, this vitamin C equals date appears in both of these. But these two are not nested models. This is not nested within this model. Cultivar only is not nested within a date only model. All right, so our classical test can't compare these. AICs can. All right, what about randomization tests? Randomization tests are going to be more complex, but it allows us to get a p-value. All right, so we can use it if we violated the assumptions and a reviewer says we need a p-value. All right, in some cases, it's good for testing if we need to account for a random variable. All right, if we need to do that, you come talk to me and I'll show you the scripts that I've used and see if it works. If we violate the assumptions though, or as our models become very complex, my recommendation is going to be to use this information criteria because it's really easy to perform. In the base package, we have something called the step function. All right, the step function will basically take the model that you start with, generate an AIC, and remove terms continuously until it gets to its simplest model. All right. So it basically does it for us. Tells us the simplest model. And there's some catches as we increase our model. And when we get to that, we'll talk about it. So that's in the base package. We also have a different package called the MUmin package, all right, that we can use to do the same thing. This is actually pretty useful because when you have a very large data set, a lot of different variables, this will generate all combinations of our models, all possible models, and compare the AIC of all of them across the board. Again, it's useful because we'll find our simplest model. So again, information criteria, we'll get the same results. If we use information criteria and these other two, as long as our assumptions are met. If our assumptions are not met, then the randomization test and the AICs will come up with the same model. And if they come up with the same model, then use whichever one's easiest to perform. So what we're going to do is work through this classical test. It's a simple model. We can very easily do this. All right, so how do we proceed? Let's step through. So we have our full model. We know cultivar and date is not significant. All right. So what we need to do is make our model that does not have that interaction term. And there's two ways to go about doing it. One is to code it in. So we used the asterisk for multiplication and R like expanded out all the terms. Well, if I use a plus, it tells R, hey, I don't want you to expand out all the terms. I just want to include these as main effects. So if I run this, and just to kind of demonstrate it, and then I look at our ANOVA table, what you will see is that our interaction term no longer exists in our model. We've removed it. So now we've created a simpler model than the full model. So that's one way to do it. The other way to do it, and one that you'll see in a little bit, is to use the update function. The update function, update, is going to update a model. So for us, we're going to update this mod.full. All right, and how are we going to update it? Well, we're going to drop a term. And what we're going to do is use the period, squiggly period sign. Because that period says, include everything to the left of the squiggly that was in this mod.full model. The period on the right is include all the terms that were to the right of that in our full model. But we want to remove that cult date interaction. And that is in the same, it is typed in the same exact way as it appears up here. Because this is how R sees our terms in the model. So I make sure I write it exactly the same way. And that's going to update the model. I'm going to save it as a new object, so mod.main, and then when I generate my ANOVA table, you will see that I get the exact same thing again. I created a model that does not have that interaction. Now for a two-way ANOVA, this is probably way overkill. But as we get to a preview of 3 and 4 and 5-way ANOVA, this is an easy, much easier way to remove select terms from our model. So we get to this point. All right. Kind of missed some stuff, but that's okay. So we get to this point. We remove the term. Now what do? Well, we look at our main effects. Both of our main effects are significant, right? Should we remove any? They're significant predictors. Both of these had a significant effect on the vitamin C. Now, we use a type 2 table. So what this is saying is cultivar still had a significant effect after we account for date. Date has a significant effect even after we account for cultivar. So both of them now are actually affecting vitamin C. All right. If we look at the summary of this model, you will see that our adjusted R squared is still at 0.54. So think about this. We were at 0.55, right? 55% of the variation of vitamin C was accounted for by that full model. When we dropped that interaction term, we only lost 1% of that variation. And what we've done now, what R is telling us, is that we could drop it. We made our simpler model. We're still accounting for 54% of the variation in these two terms. Now, if I look at I'm going to do mod wrong, and just look at date, so create this and look at the summary, pay attention to how much this adjusted R squared drops. Whoops. So yeah, 54%, 12%. Huge drop. Huge drop. What if it was cultivar? Again, it was 54%. We dropped to 40%. Still, pretty big drop. All right. So what we found is we've accounted for as much of our variation in vitamin C levels as possible without making the model too complex, without including terms that had very small effects on it. Right? So another way to look at this ANOVA table, this one, is saying that this cult date interaction is only accounting for like 1% variation, but that 1% isn't significant. The increase in our variation, in our explained variation, isn't significant enough, p is greater than 0.05, to include it in our model. All right. What about comparing our models? Well, what we've just done using that type 2 table is the same thing as if we used the ANOVA function. So ANOVA mod full versus ANOVA mod main. We get 0.2186. Where did we see that before? Where did we see this p-value before? All right, up here. We see the same thing.
Yeah, cool.
Right? So with our model simplification, what we do is we start big. We start with a full model. We look at the ANOVA table. We go to the highest interaction, that highest level. If it's significant, we stop. That interaction term contributed a lot to our model. We need to leave it in. All right? If it's not significant, drop it. Remake the model. Look at your ANOVA table to see, can we drop any more terms? And you just keep dropping terms until you get to, hopefully, that model where every term left in it is a significant predictor, where each term accounts for a significant amount of variation in our data. And we're going to be doing this quite a bit. So this is just kind of showing different ways, different outputs, demonstrating your p-values and whatnot, and demonstrating how we can use the ANOVA of the mod main and simpler models to get to this idea where the capital A ANOVA gives us the actual p-values that we would have found if we did things along with it. All right? So we've got simplest model. This is it. This is what we're working with. We need to include cult and date. Oh, and before we leave, because I think we're going to be picking up with this. What happens if we have an interaction term, but we have non-significant main effects? If you have an interaction term, you have to include the main effects of every single variable included in that interaction. So just imagine, and we don't have this yet, but imagine cult and date, this interaction term is significant. Say it's less than 0.01. But then these two are both greater than 0.05. You can't drop these two terms and only keep the interaction. Our rule is if you have the interaction term, you have to include those main effects. All right? It's a stringent rule, but it's one that we have to abide by. All right? It doesn't make sense to include an interaction term but not that main effect. All right? So we have our main effects. We have our simplest model, cultivar date. They're added together, so an additive model. Now our next step is to do our post hoc test. And what we'll do is we'll kind of pick up on this on Monday with our post hoc test. Post hoc test, and then we have practice work. All right? All right. Did you guys have any questions on that homework? Other than the randomization took a while?
How far will our test go?
Just the ANOVA. Just that homework assignment, basically. Do you have a question?
No.
This?
So, yeah, so that basically saying that cultivar and the date together are significant.
The interaction is not significant.
But individually.
Individually, they are.
Yeah, okay.
So
It just got real, like today.
this tested. What that is saying is, are these slopes parallel or not?
Okay.
They are. P-values greater than 0.05, they're parallel.
Okay.
So that means that effect, that positive effect, is positive and it's increasing at basically the same rate.
Okay.